Okay, guys, let's get started. 1 is better than 2 because there is what? A p orbital next door, right? We talk about p orbital next door, stabilizing transition state, or did I just dream this? I'm pretty sure we talked about it.
Wouldn't the ability of the leading group be dependent on the mechanism that you want to use?
Excellent question. Yes. Yes, excellent question. Excellent.
That's the answer.
I'm serious, that is a very good question. I reckon I'm assuming SN2. But yeah. Is that why we're having difficulty?
So was that.
What was the question?
He said, does it matter what mechanism we're doing? It actually does, yes. I need to revise my question. I'm thinking SN2. You're right. If it was SN1, this would be a better leaving group. You're right. So I'll take it that that's why I confused you. Okay. SN2, p orbital next door, primary p orbital next door, primary no p orbital next door, secondary. Why is 4 worse than 3? Bonding, what's the bond angle here? 60 degrees. What type of bond angle must it achieve in the transition state? 120. It's going to have a hard time achieving 120. You still can do it there. Very difficult. You ain't going to do any substitution on this guy here. That's a poor leaving group because it's on an sp2 carbon. Okay, let's see where we left off at. That's substitution. We'll pass the quizzes back into class. Substitution. Steric effects. Light off or I can't hear you. I think you said off. Yeah. We ended up above. Substitution adjacent to the reactive atom still influences. Butyl is often used for E2 elimination. Once we get to E2, we'll say that. What's the difference between a base and a nucleophile? Not too much. A base attacks an H, a nucleophile attacks something else, like a carbon. Whenever you attack an H, there's no sterics involved because attacking an H is so easy. Whenever we attack a carbon, sterics becomes more important. When you start talking nucleophiles, sterics becomes more important. But other than that, they're pretty much, it means the same thing. They're both high electron density, either very often anions. Doesn't have to be an anion. Resonant effects. This is going to be a more nucleophilic oxygen than this one. Well, this is just which is more stable. That's more stable. But stability doesn't always correlate with how good of a nucleophile it is. That's a full minus. Is that a full minus or is it delocalized? Delocalized. Yes, it's delocalized. We can do resonance. Electrons here, electrons up. And we can get this. The charge is really delocalized onto the other oxygen. The true structure is partial minus, which is more reactive, a full minus or a partial minus? Full minus. Delocalization makes it less minus. It makes it a weaker nucleophile. What does it mean to be a weaker nucleophile? It's going to be slower to do an SN2. That's a full lone pair sitting right there on the nitrogen. Is this lone pair sitting right there on nitrogen, or can you draw resonance and show lone pair over here? Resonance. Yeah, we can show resonance structure. electron density is spread over into these carbons. You can keep going. That lone pair is not just sitting on that nitrogen. Because of the delocalization by resonance, the nitrogen is less electron rich. It's a weaker nucleophile. Hybridization effects. This is a stronger nucleophile than this. Also a stronger base. Same thing up there. These are better bases. It's a better base. Why? This is a hybridization effect. This lone pair is in what type of orbital? You ever can't see, just, you know. sp3. What type of orbital is this lone pair in? sp2. sp2 lone pair is held tighter to the nitrogen. Because an sp2 orbital has 33% s, where this only has 25% s, more s character, closer to the nucleus. And this is two nitrogens, but that's the better parent. Pulls the electrons tighter. Those electrons are going to be less inclined to go do a backside attack. Jacked as a nucleophile. So that's a hybridization effect. The type of thing we saw with acid-base chemistry. Okay, let's see if we can rank these according to nucleophilic strength from weakest to strongest. These four here, which is the weakest nucleophile of those four? Somebody said water, I agree. We're going from weakest. So that's one. That means that's the weakest, right?
Yeah.
Mainly because it's neutral. All the others are anions. Forget about sodium, potassium, all that stuff. This is hydroxide. Okay? Forget about it. It's O minus. Forget about it. That's S minus. Forget about it. It's O minus. It's neutral. Okay, what's next?
Sodium acetate.
I agree, sodium acetate. That is acetate. That's two. What is acetate? That there, we just showed it up above. It's not as reactive as a plain minus because it's got resonance. What's next? OH minus or SH minus? Yes, that's three. See, hydroxide, all the minuses on the oxygen. That's going to be a better nucleophile than this where it's spread out. But what about S minus? Why is it the better nucleophile? Less electronegative, it's a worse parent. Sulfur doesn't hold the electrons as tight. Electrons are out there getting in trouble. Okay? Your body uses sulfur as a nucleophile in a lot of biochemical processes. It's a great nucleophile. It's also more acidic, and thus it can get into the minus form easier. So 1 to 4, with 4 being the strongest. Do the put these in order, 1 to 4, 1 being the weakest. Take a minute to do that. Which one's weakest? K what?
Yeah.
KF is the weakest?
Yeah.
What we got here? That's F minus. That's Cl minus, O minus, O minus, N minus, right? Get rid of those spectator ions. It looks like we're kind of going across the periodic table. O, N, F. Cl is under F. So which one's going to be a better nucleophile? Cl. F is a worse nucleophile, so that's going to be 1. It's kind of a bit of a, it's hard, we're actually going diagonal. So you're like, okay, is it better to be a worse parent or a bigger atom? And, this can be a little bit, let's do this though. That's not going to work. I was going to say, which is the stronger nucleophile, O minus or F minus? O minus clearly. Going diagonal here is sort of like apples versus oranges. Okay, we're not going straight across, we're not going straight down. Which one do you think is a better nucleophile? This is where you have to use, which one's a stronger base? No. No, HCl is a strong acid. Why? Because Cl minus likes to exist by itself. OMe is a stronger nucleophile. You can go back to which is a stronger base. I mean, 1, 2, well, we got O and O. Let's consider these. O-methyl or O-T-butyl. T-butyl is going to be boom, boom, boom. It's a tertiary butyl. Which is a stronger nucleophile? This is where the nucleophile versus base strength actually differs. This is a stronger nucleophile. Why?
Less substituents.
Less sterics. That's a stronger base though. Why?
Because there's
More donation. So this has more donation into here, alkyl donation. See, sterics don't affect acid-base chemistry. So this enhances the acidity, but it hurts the nucleophilicity. This is 3, 4.
It's the other way around.
I'm sorry. We're going worse.
You're going to stronger.
Worse would be here, here. We're getting better and better, and then this is the best. Why is that the best? Well, which is better nucleophile, N minus or O minus? N minus, because O minus holds the electrons tighter. This is the difference of sterics. Remember what we say at the very top, I believe. Sterics hurts your nucleophilic capability. This is a little bit sort of, okay, does it make sense that Cl minus is stronger than that? I mean, Cl minus is actually pretty happy just to exist by itself. It's not eager to go find something to bond to. If it was, it would bond to the H and come back here, but it doesn't. Okay. Does that help any? Do we realize or understand the ranking of those? Any questions about those? No? Okay, summing it up. What type of nucleophile can participate in an SM2 reaction? Strong ones. Does it say anything before strong? No. Only strong ones. Now, this is sort of being very general about it. In general, strong ones. There's a couple of exceptions. Yes, a weak one you might can do SN2, but it's probably going to take you like very high heating, long reaction time. Typically, you want a strong nucleophile for SN2. Why? Well, keep in mind, the nucleophile is involved in the rate determining step of an SN2. SN1, on the other hand, is the nucleophile involved in the rate determining step? No. No. If the nucleophile is involved in the rate determining step, it's going to have to be able to get in there and do something. Ultimately, it's got to be strong to do an SN2 in general. In general, which are your strong ones? Just like bases. What were your strong bases? Anions, sp3 nitrogen, sometimes sp2 nitrogen. Same thing for nucleophiles. What are your strong nucleophiles? Anions, sp3 nitrogens. But you got to keep this in mind. Your halides and your highly conjugated anions are not that strong. I mean, an F- is not that strong of a nucleophile. And acetate is not that strong of a nucleophile. But this is a place to start, and then we consider some of the little kind of exceptions that we have, just realistic things. Practice. Which compounds will lower strong nucleophiles? This one, and this one. O minus, C minus, that's cyanide. Cyanide, there's your low structure, C minus, K plus. Good nucleophile. O minus, good nucleophile. sp3 lone pair nitrogen, good nucleophile. The rest are weak. The three underlined are going to be the best for SN2. The other ones are going to be not as good, may not react at all. Or it's going to take harsh conditions, very high temperature, long reaction time. Okay, at this point, let's look at some specific SN2 reactions, make specific products. Dealing with specific atoms. The first is going to be alkylation of oxygen. Alkylation. What does that mean? We're going to do something to the oxygen. What are we going to do to it? Well, alkylate it. What's an alkyl group?
That's the carbon cell.
Carbon group. So everybody understands we're going to put carbon on the oxygen. You got to understand what the words mean, because that's the starting point. If you don't know we're going to put a carbon on the oxygen at this point, you're already behind. And the first is we're going to alkylate a carboxylic acid. Here's carboxylic acid, OH. If we put an alkyl group on, be something like this, because now there's an alkyl, an ethyl. It's no longer a carboxylic acid, that is a ester. So alkylation of an acid will give an ester. How do we alkylate this? Let's see, we've got the O. We need to put on a 2-carbon. The O can be our nucleophile. Is this a good nucleophile?
No.
Not for SN2. How can we make this a better nucleophile? Turn it into the anion form. Can we turn this into the anion form? Sure, that's called deprotonation. Remove the proton. What do we need to react this with to remove the proton? Acids don't remove protons. A base. What's your favorite base? Sodium hydroxide will work. Hydroxide will take the H, it'll make this plus water, and the sodium will sit with that guy. A variety of other bases will do this. I mean, that's, which side's favored? Left or right? Well, that's 16. What's the ppm of an acid? 4 to 5. Which side's favored? 4 or 16? 16 by 10 to the 12. You see it's highly favored. Is this a good nucleophile?
Yes.
We made our acid a better nucleophile by converting it to the, what do you want to call that species? Not the carboxylic acid, but the, not a carbanion. Carbanion is a carbon with, it's an anion. Carboxylate. Carboxylate anion. Carboxylate, like sodium carboxylate, or specifically sodium acetate. Now we got a good nucleophile. How can we put on a carbon group? Okay? This is something that's often just never realized. The carbon in the leaving group is a source of what I just circled. Because the nucleophile can attack that fragment and kick off the thing I didn't circle. Right? Now, when this attack, are we going to attack here? No, there's no leaving group there. Attack here, we kick off the leaving group. This is our SN2, right? So if we look over here, we need this fragment. That's the nucleophile. What did the nucleophile replace? Whatever your favorite leaving group is. So you got your fragment. There had to have been something there. It's a leaving group. This is the fragment. Nucleophile now bonds to it. Now it has to be a leaving group. It can't be a fragment with an H. An H is not a leaving group. So we cannot react this with just ethane. There's ethane. Can we react this with just ethane and get the ethyl group on there? No. You got to have a leaving group on one of the carbons. This is symmetrical. I mean, no matter which one. Kick something off to do a substitution. Okay? So we make the better nucleophile reacted with base. Then we put in some type of substrate in the leaving group, and we get the portion on there. The acid is converted to an ester. What do we do? What do we put on the acid? Alkyl group. Alkylation of carboxylic acids. Very basic reaction of a carboxylic acid to make an ester. Question?
Yeah, so how good of a nucleophile is the carboxylates? This is resonance. Is it like
It's not as good as something that's not resonance, but it still will react. It's going to be a little bit sluggish, but it'll react. See, we have just relative comparison. The absolute, will it react or not? Well, I know it will react. It's just not going to be as faster as something that's not resonance. Okay, another type of alkylation of oxygen. We can do this with alcohols. Problem is with alcohols, see, I knew you were going to say sodium hydroxide, so I already have it written down here. Problem is sodium hydroxide will not work with an alcohol because we're trying to make the O minus. Okay, you got it. That's O minus, right? I just see you guys all the time not understand that's minus and that's plus, just because I don't show the charges. Okay? If I showed you sodium chloride on the board, and I showed you like that, just the atoms written next to each other, that's plus and minus, right? Okay? Up there I drew the plus and minus, but that's plus and minus there too. It's ionic. So we make the minus plus water. This is 16. Which side's favored, 16 or 16? Neither, and it doesn't work. Sodium hydroxide is not strong enough to deprotonate an alcohol. Alcohols are not acidic enough. It works with carboxylic acids. You'll see down below it works with phenols, but it doesn't work with a regular alcohol if you're trying to make a non-resin stabilized O-. Instead, you have to use different bases or reagents. One is to use sodium metal. Oxidation state of 0, sodium metal. Next week in lab, when we're doing our reaction, we've got some time, we'll probably demonstrate adding sodium to an alcohol. Whenever you add sodium to an alcohol, you get a reaction. You can form the sodium. What do you want to call this species? That was a sodium carboxylate. What do you want to call this? What is this? Alcohol. When the alcohol is minus, what do you want to call it? Chlorine, you call it chloride. Alcohol, you call it alkyde. Alkyde makes sense. It's not called alkyde, it's called alkoxide. What do you call O minus? It'd be 2 minus. What do you call O minus?
Peroxide. Oh no.
Oxide?
Oxide.
It'd be 2 minus. What? Well, I'm not talking peroxide, I'm just talking oxide, right? If I put an H on it, it's called hydroxide. What if instead of an H, I put an alkyl group? Alkoxide, because there's an alkyl group on the oxygen, oxide. Okay, that's what we got here, is an alkoxide, sodium alkoxide. Now, in this reaction, you get hydrogen gas, okay? This is a redox reaction. You can balance it if you like. There's 1 H over there, and there's 2 over here. You put sodium in an alcohol, it'll start bubbling. What are the bubbles? Hydrogen gas. It's a redox reaction.
Does it not matter that sodium is like a highly soluble ion?
Sodium is a highly soluble ion.
Yeah, so would it matter? Like in its state, that state, how much it would dissociate?
Would what stay in that state?
Like the alkyl oxide, so sodium alkyl oxide.
This typically is dissolved. So it's disassociated. But that doesn't mean I can't draw it on the board like this. If you remove the solvent, it'll be a dry solid. But it will be dissolved unless you remove the solvent. The hydrogen will bubble out. It's a redox reaction. Here the sodium is 0. Here the sodium is what? Plus 1. So the sodium has been oxidized. The hydrogen has been reduced. Because here it's plus 1, but here it's 0 because it's in the elemental form there. Great way to make that's not an acid-base reaction. I'm not going to show a mechanism of taking the H. The sodium doesn't take the H. We don't make sodium hydride. It's redox, and it's probably a radical reaction. I'm not going to show a mechanism.
I'm curious, when I above it, does it not go at all, or does it just exist in equilibrium?
It does exist in equilibrium. You're right. And there's just issues with it because in equilibrium you have both of these, and when you throw in your substrate with a leading group, this can attack. So it doesn't work. But you're right. It is in equilibrium. I mean, it's a 1-to-1 equilibrium.
I just want to be sure.
Yeah. You're right. It just doesn't work practically. So down below, we can do a reaction. You take an alcohol, react it with sodium. This gives you the alkoxide, the minus. Then you throw in a substrate with a leaving group, and these electrons, bam, kick off the leaving group. And now the oxygen is bonded to the carbon instead of a chlorine. That's the bond we just made. Chlorine used to be here. Got kicked off. Good old SN2. We started with an alcohol. What type of compound did we make once we alkylated the oxygen? Put another alkyl group on it. Ether. Ether. This is called a Williamson ether synthesis. Williamson was an English chemist back in the 1800s and made a lot of ethers this way from the alcohols, forming the alkoxide and then doing a good old SN2. Of course, ethers were used back in that time as anesthetics and stuff, put people to sleep, etc. Okay, phenols. With the OHs on the benzene ring, it's a phenol. Phenols are more acidic. Why? Because the anion would be resonance stabilized. Phenols, you can use sodium hydroxide. That's 10. This is 16. This side's favored by 10 to the 6. Sodium hydroxide works with phenols, but not with regular alcohols. So you take a phenol, react with sodium hydroxide, you get the sodium alkoxide plus water. You throw in a carbon with a leaving group. Good substrate for SN2. And your O minus attacks the carbon, kick off the iodine. Oxygen now bonded to the methyl group, and we make that methyl ether. This looks pretty straightforward. Make the anion, do an SN2. Question?
Is it still called oxide even though it's a ring or
Alkoxide would be quite general. More specific, it would be called, let's see, that's a phenol. What do you want to call this? Phenoxide. Is that a good nucleophile for SN2? No. We first have to turn it into a good nucleophile, making the O minus. Because you got to have a good nucleophile for SN2. You can make some rings like this. You take this compound here and treat it with sodium, you can get this compound plus sodium bromide. What does sodium do to an alcohol? Makes the alkoxide plus what? Hydrogen gas. Sodium plus sits here. What can this do? These electrons, bam, kick off the bromine. Intramolecular SN2, internal. When that happens, what do you get? Oxygen, 1, 2, 3. I'm missing something. 1, 2, 3, 4. 1, 2, 3. Missing something. 1, 2, 3, 4, 5. Still missing something.
Your oak should bring it up.
Right there?
Yeah.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This attacks here. Kick that off. Oxygen and 4 carbons, all in a ring. Oxygen, 1, 2, 3, 4 carbons, all in a ring. We just made like that bond there. It came around and kicked off. Bromine used to be bonded here, but the oxygen came in and kicked the bromine off.
Would these happen faster once the other internal happen faster?
Yeah, internal. That's why this is faster than 1, 2, 3, 4. I mean, this is faster than this. Internal faster than reacting with another molecule, right? Typically. Especially if we're making good size rings. What's your best size rings?
6.
5 and 6? Yeah. You start trying to make like a 10-membered ring, then it might not be that good, and it may instead react with another molecule, and so it might do intermolecular. So this is an intramolecular SN2. Make sense? Oxygen, how about sulfur? Basically, everything we did with oxygen, you have the analogous sulfur reactions. Phenols, now this would be thiophenol. I'm not going to show any specific examples, but say again that your body uses sulfur for nucleophiles in a lot of processes. Your body has glutathione. This here, it's a tripeptide. It has a SH group. That SH is a good nucleophile. Even better under more basic conditions where it's S-. Your body uses that S functional group there as a sacrificial nucleophile. For example, if you get exposed to methyl iodide, it gets into your body, that sulfur can come in here. Again, it's relatively acidic. Under certain conditions, it can be S-. It doesn't have to be. It's a good nucleophile even in a neutral state. That would be an exception. But the sulfur comes in here and becomes alkylated. Methyl gets on the sulfur, right? SN2. But see, glutathione, that's its role. Its role is to do stuff like that. It doesn't serve any, it doesn't serve to make your brain work or anything. So putting the methyl on the sulfur is what it's meant to do. It's meant to react with these things and keep them from reacting with like your DNA. This reacts instead of this. You don't want to be alkylating your DNA. So it's called a sacrificial nucleophile.
Where does it come from? Which is your body make it naturally? Or?
Body makes it naturally. You can also buy it at the drugstore. Okay. It probably talks about on the bottle as detoxification or something. A lot of times there's electrophilic species that are formed in the body. Sometimes drugs become electrophilic and become reactive. And if you take an overdose of Tylenol, or too much Tylenol, you go to the doctor, what will the doctor give you? Mucomist. You've ever heard of Mucomist? It's for overdosing of Tylenol. Well, it's got an SH in it. And the Tylenol drug forms a reactive species. It doesn't form a species with a leaving group, but it becomes electrophilic. Its chemistry we'll talk about in organic too. But this acts as a nucleophile. They give you a lot of nucleophile. So that can react with the bad thing. But see, this is just a sacrificial nucleophile. Again, if you want to know more, it does an organic 2 reaction. So glutathione does that type of thing. Sulfur is a good nucleophile. When you take biochem, you'll see sulfur doing some various things. Okay, let's look at nitrogen. Direct alkylation of amines or nitrogens such as ammonia. Is that a good nucleophile or a bad nucleophile? Good. It's a good nucleophile in the neutral state because it's an sp3 nitrogen. The thing about amines is you don't have to convert them to the anion to get them to react. Amines react in the neutral state. No need to form the anion. As long as they're non-conjugated, I mean, we're talking about sp3. They're good. C synthesis of Zyrtec. On the front page, we've already looked at it a couple of times. Going from 31 to 32. First they had an alcohol, they converted it to a mesylate, which is a lot like a tosylate. Okay? Mesylate's a good leaving group. You don't have to activate it with acid. Then they come in with this amine. Okay, it's an sp3 nitrogen. Good nucleophile. This comes in, bam, kicks off the tosylate. Now the nitrogen is bonded to the carbon. But for this to go neutral, you have to lose the H. That's why they include a base. Now it took 72 hours of reflux. If we had to do that in lab, usually it takes 30 minutes in lab. 72 hours, what is that? 3 days? It's like go to lab, put it on Monday, and come back Thursday, and it's finally done. See, that's a secondary amine. It's got a little steric congestion around it with groups on it. A little surprising it took that long. Maybe they just do it over the weekend. I don't know. Now, you can do that reaction. As we just showed with that Allegra or Zyrtec, whichever one it was, you can do it. However, you do have potential problems. Putting another alkyl group on the nitrogen. You realize that was an alkylation reaction on the front page, right? Look back on the first page. The nucleophile nitrogen. Nucleophilic nitrogen. How many alkyl groups were on it in the original nitrogen compound? 2. And an H, right? Okay. Now look in the product. How many alkyl groups on the nitrogen now? 3. So in terms of what happened to the nitrogen, it became alkylated again. Alkylated. Now there's potential problems with direct alkylation of amines. That's an example of a direct alkylation. Problem is polyalkylation. Now, it's not always a problem, but sometimes it is. It's usually a problem when you don't want it to be a problem. Now, why is it a problem? This scenario tries to show that. Now, first off, it doesn't matter where the nucleophile is. Here the nucleophile is on the line, and the substrate with the leaving group is over here. This can be switched. It doesn't matter. They're both going into the same flask. I mean, ammonia is a good nucleophile. Attack here, kick that off. What do you get? You get this. The H is still there. Just a lone pair bonded there. And there's a leaving group. That's a salt. Now to go neutral, you got to remove an H. You can include a base, take away an H. To show the mechanism. A's take the H. Electrons stay behind on nitrogen as a lone pair. So, example on the front page, they included, I think, potassium carbonate as the base. Okay. Problem with this reaction is polyalkylation. Sometimes it's a problem. First off, why do you have to include a base? Why not just have the Br take the H? If the Br take the H, you would make the neutral amine plus HBr. But see, that's a base and that's an acid. This is going to come this way. Yeah, that equilibrium favors that, because that's a base, that's an acid. To get the H off, you have to include a strong base, or stronger than Br minus. Now, how do you get polyalkylation? Because ammonia, which is over here, can act as a base. If ammonia takes the H, you get ammonium bromide, and you free up your amine. Now the amine can react again And after you lose an H, you can get 2 alkyl groups on your nitrogen. That's called polyalkylation. You can actually then put a third or a fourth. Some students say, well, how can this react again? There's no lone pair. What I'm telling you is the ammonia can take the H, and you get all this equilibrium going on, and your original nitrogen can end up with multiple alkyl groups. That's a potential problem. You have to look through this, but a lot of your equilibrium is here, your acid-base chemistry, that's, you know, there's a lot of understanding that goes into that. Because of that potential problem, we'll see lots of indirect approaches for getting alkyl groups on nitrogen. To get this alkyl group on nitrogen, we could have reacted ammonia with 2 carbon with a leaving group. What's your favorite leaving group?
Iodine.
Iodine. In here, kick this off. And then you have to include maybe a base to pick up the HI. But that's a direct alkylation. Like I just told you, that can be problematic. Here's an indirect route. You can use sodium azide. Azide. Well, azide would be a Lewis structure that looked like that. It's net minus, and you got a sodium plus. I think I asked you to do azide during week 1 when we were doing Lewis structures. Azide. One of the terminal nitrogens reacts. This kicks off the bromide. Now you get the N3 bonded to the carbon. That's just condensed down. Okay. This is now neutral once it bonds, and you got a plus and a minus nitrogen there. That can be made in good yield. This is just showing an example of azide being a good nucleophile. But a common step from here is if you treat this with hydrogen and a precious metal catalyst, you can cleave 2 of the nitrogens off, and you end up with primary amine. Okay, that is a primary amine. Does it say that up here? Yeah, primary amines. Plus, you know, I'm not sure what's formed here. It may be nitrogen gas. The other 2 nitrogens may be this. Or this may come off as sort of reduced, like hydrazine or something. I'm not actually sure. But here we made this by an indirect route, and you don't have the problem of polyalkylation, because this is only going to react once here, where this has the potential of giving poly. Question?
I'm sorry, I'm a little confused on the structure of that N at the end. How would that,
Of this at the end?
no, sorry, in the middle, how that N, those 3 N's, how they actually sit?
It's just like this. This is carbon. Minus, plus. It used to have 2 lone pairs, but now the other lone pair is bonded to a carbon. Double bond here. Just like 1 lone pair is now bonded to a carbon. I mean, we just made that bond. Lone pair bonded to carbon. This nitrogen is neutral. These are plus and minus. There's no way to show it without charge, but it's net neutral. So it's alkyl N3. Everything's neutral. Well, the whole thing is neutral. So that's just azide. Of course, azides are not easy to work with because they tend to cause allergic reactions. People tend to be sensitive to azides. I've heard of a couple of people having to go to the hospital working with azides. Allergic responses. In organic 2, we'll see other indirect or alternative approaches. We'll actually see probably 3, maybe even 4 indirect routes. Nitrogen chemistry, very important. Synthesis of quats. Quaternary amine salts, often called just quats, by exhaustive alkylation. Anybody ever been to the Y recently? Worked out? Y'all don't work out, do you? Anybody work out? Uh-huh. You ever, they got the little things on the wall where you do this? What is that? Hand sanitizer? You ever read the label? What's in it?
Sodium
What?
That's alcohol.
Benzalkonium?
Phycosan.
It's a quat. It's quaternary ammonium salt. Quats have antibacterial properties. How? Something to do with the ionic nature. It disrupts the cell membrane. I don't even, do bacteria have cell membranes?
Yeah.
I don't even know. Question?
Do you think that it's a good idea or a bad idea to put alcohol in the stops? Is it a good idea?
Is this a trick question?
David, Dr. Bates was talking about it.
Talk about quats?
Yes,
Today?
last week.
Really? What was he saying? Bad idea?
He hates them.
He hates them. What do they do?
Apparently give the bacteria resistance over a long period of time.
Leads to what? Superbugs?
Yeah.
Yes. Uh-huh. I don't have an opinion. Well, now we can learn what a quad is. You take this, react with this has, it's a tertiary amine, but it still can react. These electrons here, kick that off, good old SN2. What do we get? We made that bond there, lone pair bonded to the carbon of the ethyl, kicked off the bromine. That can't go neutral though. There's no H to lose. Or it can't go neutral by losing an H. It can go neutral by sophisticated chemistry, but it's not going to go neutral easily. That right there can be isolated as a salt. What's a salt? Two ions, ion pair. There you go. That can be an end product just as the salt form. Called a, it's not primary nitrogen, it's not secondary, it's not tertiary, but it's quaternary. Nitrogen with 4 carbons. Positive charge though. Called a quat. When you get to biochem, you'll see this quat. The OH over here, what's the name of that? What's the name of that? Not choline. 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 And if you put an acetyl group on it, you have acetylcholine or acetylcholine. Y'all heard of acetylcholine? You ever seen the structure of acetylcholine? It's got the quad. I mean, the acetyl group just over here. It's got the quad. Okay. Here's the one you find at the Y, I think. Didecyl, dimethyl. Didecyl, what's that? 2 10-carbon groups? Dimethyl, 2 methyl groups. Ammonium, nitrogen with a positive called ammonium, and then there's got to be a minus to go with that. Next time you're at the Y, check it out. So quats can be made by reacting nitrogen with and getting all the alkyl groups on there. What about carbons? Can we put alkyl groups on carbons? Sure. Do we have a good nucleophile here for SN2? Typically, nucleophile for SN2, you're talking about a lone pair. I don't even see a lone pair. Can we make a carbon lone pair anywhere? Where's the most acidic hydrogen at? Right there. That's the last thing we talked about, test tube material. The SPCH is acidic enough. What base can we use to remove that and make a carbanion? N-butyl lithium? What was the other one we used? Sodamine, NaNH2. N-butyl lithium, take the H, leave these behind. We get the phenyl. Plus butane. Through an acid-base reaction, we can get a carbanion. The lithium would sit with the minus. Now we can come in here with maybe alkyl bromide, and these electrons can, boom, kick off the leaving group. Make that bond right there. The sp carbon now bonded to the sp3 carbon. Plus what? If we totally balance this, what else are we going to form here? Lithium bromide. You got a lithium sitting here. These are, and then when you kick that off, you got a Br minus that you can show with that. Plus butane. Butane was formed when you did the acid-base reaction. And so what did we do? We alkylated the carbanion. Alkylation of carbanions. How? Formation and reaction of acetylide anions. Your alkyne anions are often called acetylide anions because the simplest alkyne is acetylene. Look in the alkyne chapter for information on that. Also cyanide. Showed it earlier. But cyanide, Lewis structure is like this. And so cyanide is the carbanion. Now cyanide you can buy. Typically don't make it. It's so easy just to buy it. Potassium cyanide, something like DMSO. Show the product of this reaction. DMSO is just a solvent. It's a polar solvent. That product there. These electrons take the carbon, kick off the bromine. Well, let's look at it. How does, this is SN2 because we got a good nucleophile. How do we attack? The bromine is that way. How does the nucleophile come in? Comes in right behind it, 180 degrees behind it. So I could draw this like that. this like this and have the CN here. CN comes in over here. It pushes these groups that way. Here's your product. Does this make sense that that's the product? The CN came in over here. The bromine used to be here. Remember the transition state? Bonding, breaking. These are the same thing. Is this RS? Bromine, carbon with carbons. What is this? R. Whenever you do an SN2, what happens if the carbon that you're attacking? Inversion. So as long as you don't get any crazy priority change, this is still your top priority group. What is it now? Now S. This is 1, that's 2, that's 3. We're going clockwise, but the H is forward. That's S. R became S, inversion. What is this? It's also S. Those are the same thing. However you want to show it. But one way to get inversion is you can switch one existing Dasher-Bowl to the other. So that's what I did. That makes sense? Inversion, right? Okay. Let's look at this reaction. What type of mechanism is this? We take this 2-bromo, 3-methyl pentane, I reckon, and boil it in ethanol. Ethanol and heat. We get those products over there. Looks to me like the bromine has been replaced by the oxygen. So it looks like a substitution. You only know 2 substitution mechanisms, and that's all we will ever know this term. Test 3. They're called SN1 and SN2. Is this SN1 or SN2? Well, this is the substrate of the leaving group, right? What's the nucleophile? Both of the reactions have to have nucleophiles. What's the nucleophile? That's the only thing else up there, ethanol. Is ethanol strong or weak?
Weak.
Is it an anion?
No.
Is it an sp3 nitrogen?
No.
So is it strong or weak?
Weak.
Weak. Can ethanol do an SN2?
No.
No, it cannot. Now, perhaps, for us though, here we go. SN2 requires strong nucleophile. It requires an anion. All the previous reactions we made, we had anions or what? sp3 nitrogen. Weak nucleophile. Okay? Weak nuke. Not SN2. Unless something else tells us it's SN2. And after we get through evaluating, we say, you know what, it's got to be SN2. But let's start by saying it's not. So it's not SN2, what's the mechanism? SN1. Now, we can also see it's SN1 because if it's SN2, the oxygen should be bonded here. Because this should attack here, kick that off, oxygen should be bonded here. How would we get that product from SN2?
Out.
Hydration.
Hydration.
Yeah, but SN2 doesn't involve a cation.
SN1 does.
And 1 does. That's another reason it's SN1. First off, we're just heating it in a solvent. That's called a solvolysis reaction. And you just heat in what usually looks like a solvent. Now, since a solvent reacted, if it's more than a solvent, it's actually a reagent here. But in general, it's called a solvolysis reaction. It just looks like a solvent. Okay, it's actually SN1. What's the first step in the mechanism? Somebody said it. Leaving group leaves. Get that plus Br minus. Can a bromine just leave?
No.
Yes, a bromine can just leave. What happens with HBr if you put it in water? The bromine will leave and you will get H plus and Br minus. You learned that at Gen Chem, right? The HBr will ionize. It'll leave the H. Bromine can also leave the carbon. Not quite as easy, but we're also heating it. What type of cation did we make? Secondary. Secondaries are reasonable. I wouldn't make a primary cation. Ionization. What happens then? How do we get the first product? Ethanol. See, ethanol's weak. It won't come in here and kick off the bromine. It ain't weak enough. I'm sorry. It ain't strong enough. Ethanol's not strong enough to kick off the bromine. But once we show the cation, then the ethanol will get off the sofa and it'll attack. Weak nucleophiles can easily attack the carbocation. What does that do? Oxygen is now bonded, but we didn't lose the H and we didn't lose the ethyl. And there's one lone pair left. The other lone pair made the bond. There's a charge now. What's the charge of the oxygen? Positive. So there's that. Nucleophilic addition to the carbocation. How do we get the final product? Something takes the H. What can take it? Br minus. I'm showing HBr form. That can take the H. These electrons stay behind. We now have two lone pairs in the oxygen and we make an HBr. That's SN1 though, right? A cation. This is your rate determining step. There's no backside attack there. There's no concerted backside attack there. When you have a weak nucleophile, you're going to be SN1. Secondary cation, okay for SN1. How do you get the other product over there? Yes, what are cations prone to doing? There is an H here. These can move over. I'll go and show that over here. When that moves over, what do we get? Get plus there. Because now there's two H's here. Over here there was only one. There the carbon had 4 bonds. Now it's only 3 because there's no H there. You don't know where your H's are at. It rearranged from secondary to what? Tertiary. So that makes sense. How do we get this product then? It's the same way we got the other product. Ethanol adds and then you lose proton. I'm not going to show it out. It's the same 2 steps. Ethanol adds to get a species that looks like this and then you lose proton. So here we got regioisomers. See, SN1 often gives regioisomers through carbocation rearrangements. SN2 you never get rearrangements because there's never a cation in SN2. SN2, your nucleophile replaces the leaving group on that one carbon. The nucleophile ends up on the carbon where the leaving group was. This is the good old SN2. I'm sorry, SN1. Question?
So is it dependent on the H2O and certain product
No, the heat is probably just to get this to ionize off. Later on, we'll tell you a tricky way to help get it to ionize off. You're actually using that reagent in lab this week as a test. What was it? Yeah, silver ion. Silver will help the bromine ionize off because bromine loves silver. It's like, see you later, carbon. I'm going over here with the silver. Form silver bromide. Very strong bond, ionic bond. Question?
Is there reagents for this reaction?
No, for us, I think we said it before, anytime you can rearrange, do that. And so we would say that you're going to rearrange, and that's going to be sort of the major product. But in terms of a mechanism, I'm not asking you to decide which is major. I'm just, can you show mechanism for both? And understand that this had to come from a carbocation rearrangement. Carbocation is SN1 chemistry. Why is it SN1? Weak nucleophile. Okay, let's see what we need to do for next time. Do the reaction down here. We got some stereochemistry. It's basically a repeat up there, but what if we had stereochemistry? What would be your stereochemical outcome? You should do that. Of course, if you attack a cation, how do you attack a cation?
Both sides.
Both sides. Front and back. Be racemic. What is the rate equation for the above Solvolysis reaction? Rate equals some type of constant times what? We've already said it's SN1. So what's here? Alkyl bromide? Is ethanol involved in the rate determining step? No, just the ionization of the alkyl bromide. Just that. That's why it's SN1, not 2. That's just a review, right? What type of nucleophiles react strictly by the SN1 mechanism? Weak. Weak. Weak, weak, weak. Let's sum it up. See if this makes sense. Substrates with leaving group on primary carbon only undergo SN2. Why? Well, SN1 involves cation. Would you make a cation on primary carbon? No. Substrates with leaving group on tertiary carbon only undergo SN1. That's great for a carbocation, right? Tertiary? Why does it not do SN2? Too much steric hindrance. And remember, you don't do SN2 on a tertiary carbon. Substrates with leaving group on secondary carbon can undergo either. And if you're assessing such situation, you have to look for other clues to tell you what mechanism it's going to be. For example, if you got a secondary carbon and you have a weak nucleophile, what mechanism? SN1. So you can assess the nucleophilic strength. Okay, let's look at some other comments here. With strong nucleophiles, let's focus on the nucleophile. With strong nucleophiles, reaction will always be bimolecular. That's SN2, because 2 means bimolecular. It's also going to mean E2 when we get to elimination. So elimination bimolecular. If it's a strong nucleophile, it'll be bimolecular. Why will it always be bimolecular? Because strong nucleophiles are bullies. They're always sticking their nose into there, and it has to be involved. Okay? You got a strong bullied nucleophile. Here I come. I'm involved. It's going to be. I got to be involved. It's going to be bimolecular. I'm not waiting on you to ionize. I'm coming in backside. With weak nucleophiles, which are lazy, the reaction will be unimolecular. See, they're too lazy to come in backside and kick off the leaving group. As long as the substrate is secondary or tertiary. Because you don't do unimolecular with a primary. You don't do SN1 with primary. If the substrate is primary, the reaction will have to be bimolecular. Of course, a bimolecular reaction with a weak nucleophile will be quite difficult. Ultimately, you can get reactions where they're sort of in the borderline. And I don't want to say they don't happen, because you can actually make them happen. But you got to cook them for 2 to 3 days. It's like 200 degrees. So for us, I'm trying to give you some sort of cutoff. Let's see. Please have these worked for next time. Okay? Please have all these worked. Please also be looking at the elimination handout. I did send you by email. We'll begin elimination next time. There'll be 2 mechanisms, E1 and E2. One of them is going to be concerted. One of them is going to involve a carbocation. Very similar, except we're going to do elimination. Let me return to quizzes. The high was a 9. I think there were several 9s. I don't think there was a 10. The low was a 0.